So it's time to power up the 8080 motherboard and see just how much works. There's some basic checks we can do. First of all, we can look at the power supply, check that that's getting to all the chips, and the test after that, which I'll be doing, is to look at the clock chip. Now, there's two crystals I can see on this board. There's a crystal here which is 30 megahertz and a 74 LSO4, so that's making a crystal oscillator. And because this is a dual speed board, which I determine from the crystals rather than the other way around, that's going to give us the 10 megahertz speed, which is the 30 megahertz divided by 3. This crystal is 14.318 megahertz, and that divided by 3 gives us 4.77 megahertz, the normal speed of a standard IBM PC. So this chip here is the 8284 clock generator chip. It has a crystal oscillator built in, and it can also take an external clock input, and it has a multiplexer to switch between the two different inputs. If we look at this diagram here, we can see exactly what the 8284 does. It takes a reset input, has a Schmitt trigger, and it gets retimed off the clock to give the reset that goes to the CPU. It has a crystal oscillator which generates an oscillator output that normally goes to the ISA bus. It has this multiplexer here which can take either the crystal oscillator or an external clock, which is going to be the 30 megahertz clock, and that divides by 3 and then is buffered to become the clock going to the CPU. And then the circuitry at the bottom is to do with generating ready, which is essentially the equivalent of wait on the 8088 CPU. And we've got two pairs of inputs, ready 1 and AEN 1, and ready 2 and AEN 2. So essentially you can have two devices which can generate wait states. So let's power up the scope and make a start. Now, I've already connected my Rigol power supply to the pins where the main power supply will go. There are multiple ground pins and multiple 5-volt pins on there, so I've used my multimeter to find out which pins are 5 volts by doing continuity between one of the pin 14s of a TTL chip and the power header, and pin 7, the ground pin of a TTL chip, and the header. So now I'll switch on the Rigol power supply, program it to 5.1 volts, and I'm going to limit the current to 1 amp. Now, the reason I set it to 5.1 volts is there's going to be some voltage drop over these wires. They're a bit too thin, really. It's not a big issue when there's not a lot of current being taken, but there will be a small drop. We'll use the multimeter to actually find out what the actual voltage is. So let me power up and see what current we take. That's more than expected. Let's raise the current limit. Okay, so we're taking 1.5 amps. We've got all these chips, a lot of TTL chips. Most of those are going to take 10 to 20 milliamps, I would imagine. We've got the main chipset chips, the CPU, and we've got all the DRAM. So it's probably within the ballpark. I didn't really know what to expect, so we don't know what the board is doing at the moment. If the CPU is running, it's going to be taking more power than if the CPU is stalled in some way. So now what I'll do is I'll use my trusty Fluke multimeter and I'll measure the voltage. going to choose one of these TTL chips. This one will probably do. And we're getting 4.96 volts. That's perfectly fine. That's going to run the board without any problems. TTL chips and CPUs are specified to operate over a range of voltages. I think for TTL commercial chips it's normally plus or minus 5%, so they're going to operate quite safely between 4.75 volts and 5.25 volts. So 4.96 is perfectly okay. I could measure other places on the motherboard further away from the power supply connector just to see if there's any further voltage drop, but I'm pretty confident this is perfectly okay for us to get started. So first of all, what I'm going to do is just have a probe at the 30 megahertz crystal and see if we've got anything happening there. So there we go, that's pin 1 of the it's a 74 LSO4. And we can see the frequency is 24 megahertz. That is a 24 megahertz crystal, it's not a 30 megahertz crystal. Okay, that means this board is going to operate at 8 megahertz and 4.77 megahertz, so they're the two frequencies that are supported. And the 74 LSO4 is generating the crystal oscillator. Now, if we look at the diagram of the 8284 clock generator chip, we can see that the external clock comes in on pin 14. So let's probe that. Need to figure out how many pins it's got first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, I guess it helps if I probe the right side of the chip. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's our 24 megahertz going in on pin 14 of the clock generator IC. Let's have a look at oscillator out, which is pin 12. 9, 10, 11, 12. There we go, we've got 14.3.1, 14.315 megahertz on the scope. That's pretty close to the 14.318 that we wanted. There is a trimmer pot. No need to adjust that, it's going to make so little difference. Let's have a look at pin 8, which is the clock output. And here we go, we've got a nice clean sine wave. The ground wire is quite long, so that's going to explain some of these nasty overshoots and undershoots. But there we go, 4.77 megahertz. That's a really clean signal with good rise and fall times there. So I'm just going to put a jumper on a 2-pin header that's marked turbo, and there we go, 8 megahertz. So this is the way that the motherboard supports the two CPU frequencies, 8 megahertz and 4.77. It's got a turbo switch, and I'm pretty sure the turbo switch is going to connect to the F stroke not C input, which is the multiplexer select to select either crystal oscillator or the external frequency. So that's how the motherboard manages the two frequencies with a simple header that can go to a switch on the front of the PC once you have it in a case. So I'll set it back to 4.77 megahertz, but that's good to know that that's working. So let's confirm that the clock is getting through to the CPU. According to the datasheet, it's pin 19. Yep, so there we go. CPU is actually getting a nice clock signal. So initial checks are over. The board is powered up. There's 5 volts. The crystal oscillators are working. The clock controller IC is working. It's generating the CPU clock and it's getting to the CPU. So that's a pretty good start. The next thing to check, just to try to determine what level of operation this board has, is let's go ahead and probe the pins of the CPU and just see if they're toggling or stuck. That's going to be quite interesting. So we know that clock is working. Interrupt request is low, so nothing happening on that. NMI is low, that's good. Now we get some more interesting pins. An AD0 pin, there's nothing happening there. AD1, AD2, AD3, AD4, AD5, AD6, AD7, AD8, oh no, it's address 8, A8, A9, A10, A11, A12, A13, oops, I've probably gone wrong. Ground is pin 1, A14, A13, A12, A11, A10, A9, A8. The pins are a bit more tricky to reach around the back. Let's see what I can do. That's the reset pin. It's low, that's good, we're not in reset. So just a word to the wise, if you extend a ground pin like this and you have it such that it can drag over the circuit board, just make sure that it can't short out by insulating any exposed metal with a piece of insulating tape. So reset is pin 21 and it's low, so the chip's not in reset. For the moment I don't know what the reset circuitry looks like. I think it probably comes from a power good pin on that connector, but I'll investigate that off camera and look at that later. Now that's interesting, that's the ready pin. And we've got an interesting looking signal there. I'm fairly sure that this is part of the refresh circuitry. With 5 microseconds of division, and if we look, we're getting a ready pulse every 15 microsecond. From what I know about the way the PC works, that's the refresh circuitry for the DRAM. And another interesting thing is this particular signal comes from the timer chip, and the timer chip doesn't have a default output, which indicates that the timer chip must have been initialized because you have to program it to give you the correct refresh interval. So that gives us a clue that the CPU must be operating in some way, because it's had to initialize the counter timer chip in order to kick off the reset. Now, whether Ready has a different waveform on a working board, I'm actually not sure, so more to be discovered. The test pin is to do with the coprocessor. That's high. That's probably correct. Now, the following set of pins are interesting because they are configured for maximum mode. So, just looking at them, it's not quite clear what they do. They're not easy to interpret signals, I would say. 3 of them are status pins, 2 are Q pins, and 2 of them are for tri-states in the processor for DMA, but they probably should be toggling quite rapidly if the CPU is running. So let's have a look at them. This is QS1, this is QS0, this is status 0, this is status 1, this is status 2. Now, all of those I'd expect to be toggling in some way to indicate the CPU is running code. They're not. So that's interesting. The CPU is getting a clock. Not sure how to interpret them for the moment. Let's have a look at lock. That's high. I'm not sure how that's used on the original PC. Request grants is high. Request grant 0 is high. They're inactive. The next pin might be quite interesting. It's not read. On a working CPU, we'd expect that to be going low on a regular basis. So either the processor's not working or it's stalled in some way. This is the min-max pin. It's low. It means the processor's configured for the maximum mode. And I have another video which I plan to upload, which will explain the difference between min and max mode. SS0 is another status pin. Now we come to some pins which are dual purpose in that they change their use over the course of an access. They're the higher address pins, which are also holding status information as well. A19, A18, A17, A16, A15, and VCC, just to confirm that we've got 5 volts on the chip, 5 volts, 1 volt a division, that's 5 volts. The address pins on the 8088, a number of them are dual purpose, and again in another video I'll explain how they're used. But just to say, you can't use those pins directly. They have to go through some latches in order to latch the values, and then you have to use the outputs of the latches, which properly reflects the address bus value. Pins 16 to 9 are AD0 to AD7, address data. At the start of the cycle they hold the address value of the lower 8 bits of the address, and in the rest of the cycle they're the 8 data bits. Pins 8 to 2 and pin 39, pins A8 to A15, they actually don't need to be latched, they're always address pins. Pins 35, 36, 37, 38 are A19 to A16, and they're also status pins as well, so these pins also need to be latched, but we then know that when the chip is operating, they're going to be toggling between the address value and the status value at the CPU. So something funny is going on. So if we have a look at the pins of the datasheet, just to try and get an idea whether the behaviour we're seeing makes any sense, the ones we're interested in are reset, which is active high. We saw it was low on the CPU, so that's not holding the CPU in reset. We have a good clock, we've got good power, we know we've got maximum mode selected, pin 33 is low, NMI is low, that's active high, interrupt request is low, and that's active high. The test pin is low when used with a coprocessor. It's a source of weight. That's high, that's okay. So the read strobe is inactive, so something's stopping the CPU doing any further accesses. I'm not sure what that is. Ready is pulsing, but it's mainly high, so that normally would allow the CPU to proceed. Ready is low in order to cause the CPU to insert wait states. So that's not explaining why the CPU is halted. So that's something to be discovered in the future.